Picture this. You've been asked to compete on your favorite competitive baking show, the Great French Baking Challenge. You're in the final round, and there's 60 seconds left on the clock. And he's already finished plating his pecan tart. Then you look at your plate. Crap, you're behind. Suddenly it hits you. Luckily, you had the privilege of being in Miss Lula's 6th period AP Chem, and in the corner of the room, you see it, liquid nitrogen. Whoa, whoa, whoa. Aren't you forgetting something? Liquid nitrogen is extremely cold and can freeze tissue, causing severe damage. So make sure to wear gloves to protect your hands. Also, wear goggles to protect your eyes. Yes, they're darky.
Mix 1 quart of half and half with 1 pint of milk. Add the vanilla and sugar. Pouring the exact amount of nitrogen is tricky business. Just aim to pour for about a liter of it. Keep stirring until you have a consistent mixture.
Now's the final moment. You won the baking challenge. You did it. Turns out your chemical gastronomy skills were up to snuff after all. Too bad the prize is a year-long supply of baguettes.
All around me are familiar faces.
An explanation of how liquid nitrogen ice cream works. Some background on liquid nitrogen. Liquid nitrogen is a colorless, clear liquid first liquefied by 2 Polish physicists in 1883. It has a density of 0.807 grams per milliliter, a boiling point of negative 195.79 degrees Celsius. It is a cryogenic fluid, meaning it can freeze things quickly, which is especially useful for making ice cream. Used for cooling things very quickly, but not for long periods of time, it immediately evaporates when it comes into contact with anything warmer than itself, which is seen experimentally when liquid nitrogen is poured and vapor escapes the container.
So, liquid nitrogen is known as one of the best methods to make ice cream because of how fast it can freeze the liquid in the base of the ice cream. It is used as an emulsifier because it combines the elements in order to create ice cream. A stabilizer like gar gum and karo gum, which we do not use, can be added to the mix to prevent the ice cream from melting quickly.
The ingredients work in 4 main ways. Ice crystals, which are formed when the liquid component of the ice cream base starts to freeze, add to the texture of the ice cream. Fat globules, individual pieces of intracellular fat inside other cell types than fat acids like milk and half used. This makes the ice cream more dense. Sweeteners add to the taste and body of the ice cream in sugar form, like the vanilla used. They effectively lower the freezing point of the ice cream. And air, the cells added to the base of the ice cream, change the consistency. This can make the ice cream fluffy or airy.
This is how phase changes explain the phenomenon of liquid nitrogen. Liquid nitrogen is a good example of a gas that can be in a liquid phase. Liquid nitrogen is made by liquefaction of the atmospheric air, usually through compression or cooling. Liquid nitrogen evaporates when it's in contact with a warmer gas, resulting in that vapor seen when liquid nitrogen is poured, which surrounds the liquid, demonstrating how it exists as a gas at the liquid phase.
The way to understand phase changes through diagrams is understanding the 3 phases involved: solid, liquid, and gas. Phase changes have an x-axis of temperature in degrees Celsius usually, and a y-axis of pressure, sometimes in pascals or bars. You'll see in the next couple of slides that we use bars to measure pressure. There are 3 regions on phase diagrams representing the respective phases. If you change the temperature or pressure, the phase will understandably change, as it is moving to a different region. If the line between the solid-liquid regions is negative, the density of the liquid is greater than that of the solid, like water, which is why ice floats in water, because the solid phase is less dense than the liquid phase. Nitrogen solid-liquid line is positive, however.
There are 3 important features of a phase diagram. The critical point, or a point on a phase diagram at which both the liquid and gas phases of a substance have the same density and are therefore indistinguishable at a temperature of negative 146.95 degrees Celsius, a pressure at 34 bar, a density of 314.02 kilograms per meters cubed. The triple point, as known as the temperature and pressure at which the solid, liquid, and vapor phases of a pure substance can coexist in equilibrium, is at the temperature of negative 210 degrees Celsius and a pressure of 1.252 times 10 to the negative first bar. The supercritical region is known when nitrogen is a supercritical fluid when its temperature and pressure is above its critical point, which is any region beyond a temperature of negative 146.95 degrees Celsius, pressure at 34 bar, and a density of 314.02 kilograms per meter square cubed.
This is the phase diagram of nitrogen. As you can see, the triple point is lower than usual, and the critical point is also lower. The region labeled the supercritical phase is where nitrogen exists as a supercritical fluid, and the certain regions labeled solid phase, compressible liquid, and liquid phase, and gaseous phase represent the different phases in which nitrogen exists at the different temperatures and different pressures.